Okay, whenever you're ready.
All right, thanks, Tamara. Okay, so I'm sorry, but I think one of the effects of doing things on Zoom is that you're right. You'll see another big mistake, but the fact that no one notices says something about the effectivity of Zoom. Anyway, I had this theorem last time, and I talked about the method of its proof as a motivation. Everything was fine. And then I'm going to put now the second slide that was just next to it. And this is what I had as the steps for the proof, which is fine as long, unfortunately, there was another step. I will not say anything about this. But unfortunately, as written, it doesn't make sense. The jump from 1 to 2, because I skipped the whole step and the whole point of my problem set was exactly the part that I skipped. So let me put this down. And what was missing is the next step, which is due to Dave Marker in a beautiful paper from maybe the late 80s or mid 90s, I think, or early 90s even. And this is this step. So Udi showed that it's enough to look at one variable functions. And now we are assuming that R is not definable in K. And remind you, K is the expansion of the algebraically closed field by O minimal sets. And what Marker showed that if you cannot define the reals, if you cannot define R, then actually you cannot define any set which is infinite or co-infinite. You cannot define any set unless it is either finite or co-finite, unless it is finite or co-finite. And it follows quite easily from that. So if you assume that R is not definable in K, it means that this structure, the expansion of the algebraically closed field by the extra stuff, is strongly minimal. This is what was missing. And that's why the next step 2 starts from if K is strongly minimal, then blah, blah, blah. Okay, so otherwise the whole rationale does not make any sense. And this is exactly what I took the heart. It did things over the real and semi-algebraically, but everything works in arbitrary or minimal structure. And I think it's a very beautiful argument, definability argument. You don't need to know much model theory except basic definability. And this is what I wrote down as problem set 1. I really suggest, especially for young people, to see the argument how you produce in the O-minimal setting from an infinite, co-infinite set inside the complex field or just the algebraic closure of R, how you produce actually the real line from that. It's quite remarkable that you can do it. It's all very geometric and hands-on argument. So I send you to take a look at that. All right, so this is what was missing. And again, I implore you to stop me when I make a nonsense like that. Please stop me if something doesn't make sense. All right, so now, where is it? Let me talk, before getting to O minimality, let me talk more generally for a bit about topological fields. And I will, okay, so yeah, it will appear twice and then it will no more appear twice. You know what, this is bizarre, so I will write it. I will leave this and now write. Okay, so what is a topological field? A topological field is like a topological group, but with a bit extra. So topological field is a field, first of all, F, with a topology tau, such that, well, all the operations, x plus y, x minus y, x times y, these are functions from f squared to f, are continuous. And when we say continuous, we view f squared with the product topology, with respect here to product topology. Second thing is that 1 over x is continuous from f without 0 into f1 without 0. And third, usually they don't want the topology to be trivial, so there is U open, which is neither the field nor the empty set. Okay, and right away, unlike the case with topological groups, so I can put here a bunch of exercises. I don't want to go deep into it. All of them are very cute, and I enjoyed spending time on them for myself. So one is the tau, any field topology is necessarily Hausdorff. Right, for groups you have to add this, Hausdorff. Second, which I think is less trivial, today it took me a while I needed help even for that. If F is compact, then it's necessarily finite. If anyone has a fast proof of that, F is finite. And I think along the way, you might want to prove that 1 over x has no limit. Maybe before 2, 1 over x has no limit at 0. 0. And now what I want to do is go through a bunch of examples. Some of them will later feature in the work on all minimal structures. So let me start with trivial examples. So finite fields, but then with the discrete topology. Necessarily, it's Hausdorff. Finite fields, so of course discrete topology. Now linearly ordered field, which is already in our realm. Linearly ordered field. So these are fields with the axioms that say if x is less than y, then first of all, it doesn't matter what you add, z plus x is less than z plus y. And the second thing, if z is greater than 0, then also zx is less than zy. And this is enough to guarantee all the requirements that I have on the left here. So again, it's an exercise to show that this is a topological field. All these are cute problems to work on if you're not familiar with that, or even if you are, because, all right. Yeah, this is fine. And now if F is any field, doesn't matter, with no topology in it, we can look at the formal power series over F, just power series with taking powers in Z, but Laurent series, so not only power series. Okay, so let me write it. Okay, so this is what's called the Laurent series, or a k t to the k, and you allow k to start with any negative integer and a k in F.
Sorry, Kobi, may I interrupt you with a question?
Yes, yes, please.
It's on your first slide here on the left.
Yes.
I don't get either the definition or the exercise. For example,
which one?
I don't know. I don't know if I don't get the definition or the exercise, because, for example, if is the real field with the classical structure and the classical topology, do you consider it as a topology?
Yes.
So the exercise. So you say that all these facts are true, right? In a topological field.
Yes.
So I don't get why a compact set should be finite.
No, the field. If the field is
itself.
compact.
Okay. Okay.
If F, the field, F is the field, not just any set.
Okay. Right.
Yes. I'm not claiming that there are no compact subsets.
Okay.
Of course.
Okay.
Yes.
Okay. Sorry for the interruption.
No, I'm glad. Please interrupt. Otherwise, I feel like I'm talking to in my. mother's apartment to the walls. So
don't encourage
please
me.
Interrupt. Always interrupt me.
Okay. Thank you.
Sure. And then, of course, as I think most of you know, we have evaluation taking in Z infinity, and the valuation of an element is the first K such that AK is non-zero. I will not talk, so you get a value, and then V of 0, sorry, is plus infinity. And we get so-called evaluation topology, and then I guess the valuation, the basis for the topology is, let's see if I'm getting it right, f of, let's say n, and you look at all the G, such that the valuation of G minus f is greater or equal to n, and this is a basis for field topology. Again, there is something to prove here, of course, that this is a field topology. I will just comment that if you view F inside K is closed, and the induced topology is discrete. Okay, and now a case that we are interested in and will come up all the time is when you start with a topological field, and you take an algebraic extension, F alpha, where we assume that F alpha, or F alpha has finite degree. Then in this case, just like the complex and the reals, we know that we can identify F alpha with F to the n. F alpha is a vector space over F of dimension n. And we can also, it also equals, and this is the way we do it, of course, to the polynomial ring F alpha. And there is, we just associate to every element of Fn a polynomial with F, where alpha is plugged in there. And it turns out that F alpha with the product topology now, with product topology coming from F, is a topological field. Okay, and showing continuity of plus and times is not hard, because again, the imaginary and the real part, if you want, the coordinates will be polynomials over F, but showing that 1 over X is continuous is less trivial, but still it's not a difficult exercise to show. And of course, the main example we have in mind is our standard situation. We look at R extended by R minus 1. By square root of minus 1, R is an ordered field, it's topological, and we view it with the product topology on R square, and it becomes a topological field. All right, and now we can, one can develop the whole theory of topological field. I'm not going to go in this direction, but let's talk about differentiability in topological fields. And we'll see how far we can push this in without any definability, you know. Okay, so what's you know what? I'll start. I'll move to this. I'll move to this page, and I'll start it here. So definition: F a topological field. And we have a point. This will appear constantly in our setting. We have a point inside an open set, inside F. All my U's will be open, and we have F from U to F. Just a function, right? No model theory. yet. And F is called differentiable. I will sometimes say F differentiable, but let's say that we have only one field around, differentiable at x0 with respect to x. Just the usual thing. If there exists some element D in F, such that the limit of the difference expression divided by h as h goes to 0 is equal to D. But of course, the limit with respect to the topology, so which means that something like that, for every open neighborhood of 0, like epsilon, there exists another open neighborhood of 0, such that for every h in V, we have what happened here? We have f of x0 plus h minus f of x0 over h belonging, sorry, minus D belongs to U. Right? And I'll just comment that if there is a basis to the topology which is definable in some setting that we work with, then this property is a first order property of your function. You can locate all the points in which a function is differentiable just using by quantifying over a basis. Now, there is another way of saying it, right? In one variable, it's always very simple. Equivalently, there is an F linear map T from F to F. Actually, for us, the map is x goes to dx. This is what we're aiming for. Such that the limit as f of x0 plus h minus f of x0 minus t of h divided by h, all in the field as h goes to 0 is 0. Okay, in one variable, it's exactly the same. To say in higher variable, there is an issue, continuous partial derivatives, etc. But in one variable, it's simple. All right, and we'll remember that it will be useful in a second. And just based on this standard calculus definition, it turns out you immediately get, just like you do in your calculus class, you don't need anything else. You get all the very basics. So first of all, you get that f differentiable implies f continuous at a point, and you get the derivation rules. F times g prime is f prime g plus f g prime, everything from calculus classes you get just based on topological field, axioms of topological field. If you remember, the proofs are nothing. Now, I should say, I try to think a bit about the chain rule, and I don't know the answer. If one can do it, can you get the chain rule like that? Let me describe the problem. The problem with the chain rule is not to get the right formula, but to show that the composition is differentiable. So I don't know if it's true or not. In this setting, I looked quickly. There's not much literature on topological fields. So let me write it this, f differentiable at x naught, g differentiable at f of x naught, does it follow? I don't know the answer, that f of g is differentiable at x naught. For actually, embarrassingly, for a while, I was teaching a wrong proof. There is a very elementary proof of the chain rule if you taught calculus. And there were like 2-3 years that I was giving just this elementary proof until someone asked me, why can you divide by 0? And I realized that actually, if you taught this, the chain rule, the proof of the chain rule is tricky a bit. Again. Okay. All right. And now let me again do examples, right? And again, you get the basic examples are just very formal, right? So if you have any field, every polynomial in fx is differentiable in a topological field, and its derivative is just the formal derivative. Is the formal derivative, and the same for rational functions, of course, but they will be differentiable only away from the places where the domain, away from the zeros of the denominator. Let's look at the second example of the power series. So if K is the power series field, and now, of course, polynomials, everything is fine with respect to K, but now let's look at formal power series now, with whose valuation is greater than 0. So h of 0 is 0. So it's not hard to see that if you, maybe this was done even in one of the classes on trans series somehow, or I'm not sure if you look at the neighborhood of 0 of all the elements whose valuation is greater than 0, then h actually gives rise to a function from u to u, is well defined. Differentiable, K now, right? Differentiable with respect to K differentiable, this is our field. And its derivative is again the formal power series, the formal derivation, yes? So h prime x is just the formal derivative term by term of the power series. So everything works as smooth as we can expect. And now let's say something about finite extension. So again, but now I added the assumption F ordered field. I'll say in a second why. I'm not sure if you can do it in topological fields. In general, something I needed the field to be ordered. I will say why. And we have K F alpha, which we identify again with F of F to the n. So I'm assuming that the degree of F of K, sorry, is n over F. So we have a finite extension. And now we have F from some open set inside the finite extension into K. And x0 is a point in U. Okay, then the following are equivalent, and this is again quite elementary, almost from definitions. I will try it, I'll say what. One, F is K differentiable, right? The field we are looking at is the finite extension. So F is K differentiable at x0. And the second, so F is a function from K to K. So F is also a function from Fn to Fn, right? So we identify, we can think of F as a function from Fn to Fn. As such, it is F differentiable. So now I have to define what it means. I'll say in a second. Let me put it. You know what? No, I'll say exactly what I mean, F differentiable. And it is exactly, I'm just copying the definition from basic calculus that we're studying. So what is this? That there is a T from Fn to Fn. So, but Fn we identify it with K. So K is an F vector space, which is F linear. And this is going to be the differential of the function, such that the limit of this, now these are elements of F to the n, right? So we are now adding and subtracting in F to the n minus T of H. And now we divide by the absolute value of H. And this is the only way I could make sense of this definition, because H now is an element in Fn. This is in Fn. So I want to make sense of this. I need absolute value. So you can take the absolute value with respect to the Euclidean absolute value, sorry, or the maximum absolute value, it doesn't matter, as h approaches to 0 in Fn should be 0. So f can be approximated by a linear function, f linear function from Fn to Fn. And in addition, this linear function is not an arbitrary function. T is also k-linear. So it's a, right, Fn is a vector space. So K, sorry, it's a vector space over F. Linear functions can be F linear functions, but for F to be differentiable in the sense of the finite extension, the differential, right? This is like the differential of F. The differential of F at x0 has to be also k-linear. Right? Among all the F linear functions from Fn to Fn, there are some which are also k-linear, which is much stronger, of course. It just comes from a multiplication by a scalar. And we know this actually very well from, and this is very simple to prove, 1 and 2. Almost 1 implies 2 almost by definition, by the second definition that I had, sorry, of differentiability. Where is the second definition? Sorry, here. This definition of differentiability basically says that we have here F, right? F here is K here. This is the field we are looking at. So one direction is immediate, but also the other. Both directions are almost immediate. Now, let me go back and remind you that we know this condition in the cases that we are interested in. So if K is F added -1, you don't even need to assume real closed or anything, then the differential of F, written as a matrix of F, which is what we call T, written as the matrix with respect to the bases 1 and I, with respect to bases 1 and I, and this is the usual identification of such extensions with F square, is just df dx1 df1, sorry, dx1, df1, dx2, df2. So I'm looking at the coordinate function, dx1, df2, dx2. And now you play a little and you ask yourself, okay, what kind of linear functions like this from f squared to f squared are k-linear, and it's enough to see that they commute with I, is exactly of the form A minus B, B, A, right? These are the k-linear. These are the k-linear matrices. So just under the assumption of F an ordered field and K is the extension of F by square root of -1, we get the Cauchy-Riemann equations for functions which are differential with respect to K. Okay, so we get, now not to be confused with a stronger statement that says that partial derivative exists and they satisfy the Cauchy-Riemann equation. To say that the map is differentiable in the sense of Fn is stronger than saying that the partial derivative exists. And there we usually need continuity in order to get the equivalent continuity, sorry, of the derivatives. I'm not claiming, I don't know if this is true or not in this setting, general setting, but I just wanted to make a point that getting Cauchy-Riemann is really very elementary. It's all part of the elementary theory that works in almost any topological field. You don't need any fancy completeness, local compactness, none of this is needed to get the differentiability inside the extension inside K is differentiable if and only if it satisfies the Cauchy-Riemann equation. And now I leave it as a question, how much can one develop the theory on this level of generality? I don't know. I think I will stop here, this level of generality. How much can this be further developed in this general setting of topological fields? I don't know.
So, Kobi?
Yes.
So for you, you consider only the partial derivatives only in the case of differentiable map, right?
Yes.
Function. Okay.
Yes. Yeah. Yes. Because so in particular, I didn't write it that if it's differentiable, you can show that the partial derivative exists. This is the easy direction.
Okay. Okay.
Yes. 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 So now what I want to do is just before we move to the theory, let's go back to O minimality now, finally, to O minimality. And let's look at examples and which definable functions are differentiable, of course, not on R, but on K. So we have R O minimal, expanding a real closed field R, and K always is the algebraic closure of R identified with R squared. And R is just a real closed field. All right, so of course, just like we had before, we get a topological field on K. The product topology we saw is always on finite extension. So any K rational functions, and I will only talk about definable functions now. So they will all be definable, even if I'm not saying, we'll see why they are. And this is just definable in the field, is K differentiable on its domain, right? We saw it's true always, just formally. The derivative is the formal derivative. Now let's talk about the structure that I'm sure Gareth discussed, which is R sub n. The expansion of R with all restricted analytic functions, right? Gareth talked about it. All right, and now let's point out the following. So we work over the reals now, yes? Just R plus times and all restricted analytic functions. Yes. Okay. But over the reals. So now if we have H, again, a formal power series even in C over C, which converges, converging in a neighborhood of some Z0 in C, then I'm saying there is always some U open. All my U will be open, containing Z0, such that H restricted to U is definable in R sub n. Why is that? Because the real and imaginary part of H will be real analytic functions defined in some neighborhood of Z. Z now will be viewed as a point in R squared. And real analytic functions, converging power series, sorry, are always definable on at least on some closed interval containing, or a closed box containing Z0, yes? Just because since real and imaginary of F are real analytic. So the point is, already we see that any germ, so if you want, we'll say not any germ, a germ of every analytic function, C analytic, right? We're talking about the classical. When I say classical, I always will mean over C. C analytic function is definable in R sub n. And in this sense, what I said last time, when we develop the theory of definable functions in arbitrary or minimal structures, we will in particular recover the local theory, at least, of every analytic function, right? Because every analytic function is definable locally in some neighborhood of your point in R sub n. So let's remember that. Now let's talk about the other extreme in some sense. Let's look at e to the z from C to C. And I think you all know that it is not definable in any omnimal structure. But let me just, in order to write some full proof of something, let's write a proof of the following, slightly stronger, that let U C be some open set, open. E to the Z restricted to U, definable in some, we don't care any, O minimal structure over the reals, of course, everything is over the reals. Then what should be the conclusion? What can we say about U? What kind of open sets you can have? You can hope to have the exponential function definable on. The imaginary part of U has to be bounded. Okay, so far I didn't say it is definable, but if it is definable in any minimal structure, then we are forced to have the imaginary part bounded. And why is that? We define g of z to be e to the z divided by absolute value of e to the z. Of course, if e to the z is defined, then this is defined. And this, right, we know if we let z equal to x plus iy, it's just e to the iy, right? Because e to the x is the absolute value, is the modulus of absolute value of e to the z. And now we consider the set or y in R such that e to the iy, which we have now in our hand, equal to 1. And this is contained in 2 pi z. And because 2 pi z is an infinite discrete set, thus has to be bounded if it's definable in an omnimal structure. That has to be bounded because of omnimality. So, sorry, I see that we could have a priori, yeah, this does not exactly prove it, right? Because we could have a priori, no, sorry, it's an infinite set, it is definable. So, but what bothers me is that we could have y going into the y-axis and not intersecting it. It just says that the intersection with the y-axis is bounded. No, sorry, this is the imaginary part of y, right? This is exactly what I want to say. Do we get it, that it's bounded? Now I don't believe that we prove that the imaginary part is bounded. Let me. Yeah, I guess it's a little bit more subtle because what? Because I think it follows that the projection, yeah, this is true, that the projection of u onto the the y-axis, yeah, maybe this is no, sorry. It's okay. Why? Let me see. We have, we have G goes from U into C, and so from here we get, and we showed that there are only finitely many, let me write it like this, xy in U such that iy belongs to 2 to the pi z. So we have, and because of O minimality, we cannot, if U were bounded, if in U was unbounded, then the projection on the y coordinate will contain an array, then in U intersect 2 pi z is infinite. Sorry, I just, of course. All right, sorry, it's simple. All right, so we do have that if e to the z is definable on any open subset of C, the imaginary part has to be bounded. And indeed, conversely, we show, and in Rnx, sorry, I have to finish. Okay, in Rnx, e to the z restricted to, no, when do I finish, Tamara? I'm sorry, I'm finishing today at
12.
The round hour?
At 12, yes, at 12.
All right, okay. Then in z, let's say in between minus bb on a strip is definable. Why? Because you only need, because e to the z is e to the e to the x cosine y plus I sine y, and these are definable in R sub n, on the interval minus b. And this is just real function. Okay, so in Rx, we can define it on any strip. And the little fact I showed before showed that you cannot hope for anything better. You can only define it on strips. All right, and notice that if the strip is large enough, right? So if we look at e to the z restricted to the strip imaginary part of z is less than pi, then we get a function. Well, you know what? Let me do it injective. So let me write it like this. If we do it, imaginary part of z is less than pi, greater or equal to minus pi, is injective. So we can define its inverse. And we have a branch of Lanzi, which is almost like a global and entire function. Of course, it's not. But if we want it to be differentiable everywhere, then we will do it on C, let's say minus R less than or equal to 0 into C is definable and of course differentiable. Okay, so we have quite big functions, right? Definable new functions, transcendental functions, which are definable in O minimal structures. there is a nice question that maybe I should maybe at least mention, question that some people worked on and assume that f from V to Rn, from V inside Rn, real function, into R is R analytic and definable in some O minimal structure, indefinable in some O minimal R. When can it be? When, or what do we need to know about R, this O minimal structure R? When can we extend it definably? Extend it definably to some F hat, let's say U in Cn into C, which is analytic. Of course, it is not true in general. For example, e to the x is not defined, cannot be extended without sine and cosine, but there is very nice work of Kaiser and his recent student Opris, I think I'm saying it right, on such function, on such questions in RNX, where they get some strong results, and especially in the PhD thesis of Opris, there are strong results on certain families of functions where you can do it definably. Okay, let me just end with, I will do the last example next time, but add with another example, another question I could say. In RNX, we said, well, even in Rx, we don't need, I'm putting n here. We have e to the x going from R to R. And then in elementary extensions, we can define, we can take some, let's say, alpha infinite and look at e to the alpha ln x is definable, which is just x to the alpha. So we have like a power on infinite of an infinite power of x definable. You can ask yourself, well, can you do something similar in C? Is there a definable z to the alpha from k to k for alpha infinite, which is definable in O minimal structure, I mean, which is k differentiable? Can you play the same game we did with real functions? Can we do it with complex functions and get infinite powers of z which are definable? Now notice that in non-standard analysis, if to the model theorists among us, of course you can do it in non-standard analysis, because you can look at a polynomial, not a power, just a power with an integer, a non-standard integer. So in non-standard analysis, I'm just putting it as a side remark. Analysis, this is done, this can be done, but this of course will be model of which will have also the integers in it. And we can get what they say x to like a star finite polynomial. I'll write it with z, and just because all the powers were differentiable, right, for n star infinite. And this will be k differentiable with respect to the elementary extension of the complex numbers. So the question is, can we do the same thing in O minimal structure? Within the O minimal structure, can we have a k differentiable function in elementary extension with an infinite power? We'll talk about that. All right, so this is a good time to stop, and I will hopefully continue on board on Wednesday.
Thank you, Kobi. And let me mention that Opris, the student of Kaiser, will be giving a talk in geometry and model theory seminar, probably about what you mentioned. Let me see, I believe next week.
Ah, great timing.
Let me just check. Yes, next week. On Tuesday.
Nice. Okay, so it's a perfect timing. It was great. Okay, so I will see them, I guess. This will be in person? No, I guess on Zoom, right?
Oh, no, he will be on Zoom. He is not here. Yes.
I see. Great.